Hi, I'm Randall Heyman. This is my, I think, 161st Corona help video. If you'd like me to make a video for you, then just email or comment below any of my videos. So this is for Benny, who's in California. They've had some bad fires there, and also they've got problems with COVID, like a lot of places in the world. So I hope, Benny, you are doing okay, given all of that. Anyway, you asked me to talk about dihedral groups, and you've asked some specific questions, which I'll take at the end. But I just wanted to try and, I've actually got a lot here, so we'll just have to see how this goes. So what we're basically concerned about is rotations and reflections in polynomials. So let me just get this going here. I'll draw a nice triangle here, and we can start. Okay, here's a triangle. I'm going to label this, I'll call this corner 1, corner 2, corner 3. Now, there's two sorts of movements we're concerned about here. We can rotate around this center here, and we can rotate by 120 degrees or 240 degrees. And in that way, the triangle will, when we rotate it, will be in the same position. So let me just say here, let's say what we're going to do is I'll use two-line notation to indicate what's going on here. I'm going to rotate it. I'm going to call this sigma, and sigma is a rotation of 120 degrees. So if I've got 1, 2, 3 here, 1, I'll put underneath, 1 will become 2, 2 will become 3, and 3 will become 1. And what will it look like once I've done the reflection? Well, whoops. I might have to start drawing the triangles. I think maybe I'll try and draw the triangles myself rather than using my little gadget there. Okay, so let's draw the triangle. Let's try and draw it a bit bigger. I'm going to have trouble here because I'm going to have to draw a lot of triangles. Okay, so what happens is this one becomes 2, this becomes 3, and this becomes 1. Okay, now the other thing that we could do, I'll go back to my little gadget for this bit. Now, the only other thing that I'm concerned about here is reflection. And here we could reflect in this line here, which I'll call L1, or we could reflect in L2, or we could reflect in L3. Now maybe, actually let's call this one L1, let's call this one L2 and this one L3. That's a little bit more sensible. Okay, so we could do, I'm going to use tau to indicate a reflection, and here I'll put 1, which means a reflection in this line here, L1. And so what will that do? Well, 1 will stay 1. When I reflect this here, when I reflect on this line here, 1 stays where it is, but obviously 2 becomes 3 and 3 becomes 2. And let's draw the triangle after the reflection. We're going to have 1, 3, 2. Now, what's actually happened, if I actually did, I've drawn the actions here, but if I actually kept them on the same spot, you'd see that the triangle remains the same. I haven't stretched the triangle, compressed the triangle. I haven't even moved the triangle. If I didn't have numbers on it, the one numbers 1, 2, 3, you wouldn't know there's been any change at all. Okay, so I suppose there's one other action that we're going to have to discuss, and that's this one. And I'll call this one, I'll call it the number 1. Sometimes they use E, and it's basically no change. So 1 becomes 1, 2 becomes 2, 3 becomes 3. 1, 2, 3. Okay, now that's all fine. I mean, you could see, for example, that if I take this one 3 times, do it 3 times, I'll end up with this one down here, the unchanged one. Anyway, you might ask, are there any other things that are in a similar vein? And the answer is no. What I'm specifically talking about here is isometries. So isometries that are symmetric. So if you want to see a proper full mathematical definition of what I'm talking about here with these rotations and reflections, then you're going to look up the word isometry and you're going to work up the word symmetry or symmetric. Okay, so this is from Lagrange multipliers. Let's rub this out. Okay, so the question is, what are all the possible ways of manipulating this triangle? Well, before we do that, let's write a definition. So for n greater than or equal to 3, the dihedral group dn, we call it dn, is the symmetries of the n-sided, or regular-sided, I suppose, polygon. N-sided regular polygon. So just when I say regular, I mean here, I'm saying that all the sides are of the same length and all the interior angles are the same. So we're talking here about squares, the regular pentagon, the equilateral triangle. So I've started out suggesting D3, or explaining a bit about D3, the dihedral group of the equilateral triangle, but there's also ones for all the polygons, regular polygons with more sides than that. Now for n equals 1 and 2, they're still dihedral groups, but I'll talk about them. You can't really make sense of the symmetry of a 1 or 2-sided polygon. So I will talk about that later. Okay. Now, what I wanted to do was actually look at all the symmetries of the equilateral triangle. So what I'll do is, just see if I can do this neatly. I suppose I should have done this beforehand, but that's not really the spirit of these coronavirus. Not really the spirit of these coronavirus videos. Okay, so what I'll do is I'll put one there, so that's 2. 3, 4. Lift this up a little bit. 5 and 6. Okay. So this is the central one. This one here, I'll label it here 1, 2, 3. Okay. So I suppose the first thing that we could do is we could do what I called 1, which is 1 becomes 1, 2 becomes 2, 3 becomes 3. So this is the triangle is unchanged. The next one I could do, which I did, was sigma, and that was a rotation of 120 degrees. So 1 became 2, 2 became 3, 3 became 1. So 1, 2, 3. The next one I could do is I could do sigma squared. So I do it twice. 1 becomes 2. So 1 becomes 2 becomes 3 when I rotate twice. So 1 will go to there. So the 1 here goes around to here, the 2, and then it goes around here to the 3. So similarly, 2 goes to 3, goes to 1. So 2 goes to there. And 3 goes to here. So if I wanted to write it using what's called this two-line notation, we can see that 1 has become 2, 2 after the 2 rotations has become 3, and 3 has become 1. Okay. The next thing we could do is a reflection in, so this is L1, the line 1, L2, L3. So tau 1 is the reflection in the line L1, which is what we did when I started this video. So if we reflect the triangle in the middle, if we reflect that in this line here, L1, well, 1 will just stay 1, 2 will become 3, and 3 will become 2. So 1, 3, 2. And of course, we can reflect in line 2 and 3. So let's just quickly do that. If we now go to L2, we're going to reflect there. Well, 3 will stay the same and 1 and 2 will swap. So 2, 1, 3. And then this one up here, tau 3, we're going to reflect in this line here, L3. And so 2 will stay the same. So 2 stays the same, 1 becomes 3, 3 becomes 1. So 2, 3, 1. Okay, so what we've said is that what I've shown you is that Dn is actually the set 1, sigma squared, tau 1, tau 2, tau 3. And so the number of elements, or the cardinality of D3, is 6. And you'll see that works in general. D of n is equal to 2n. You might like to prove that if you're keen. Now, there's another way to look at this, which you'll see often, and that is that let's I'm just going to use tau now, and it's going to be, you can consider it tau 1, but whatever it is, I've fixed on it. It's a reflection in L1 that I'll use. And what we can say is that, so actually up here, I should have written D6, not Dn, sorry. So it's for D6. So D6, sorry, this is not D6, it's D3. D3. Okay. So another way to say that D3, it is generated by sigma and tau. And what do I mean by that? I mean, if you do sigma 3 times, you'll get 1. So because the generator means we can use it, we use these repeatedly, these elements. So we've got 1. Clearly we've got sigma because that's the rotation, which is here. We're just taking that's straight out of there. But obviously using this sigma, we can generate sigma squared. And then we've got tau. And then what we can do is we can write sigma tau and sigma squared tau. And if you go back and work this out, you'll see that these are what we were calling tau 2 and tau 3. So there's this interplay here between here, I suppose, let's just have a look at here. What I'm saying is that if we take the triangle and first we apply this bit here, the reflection in L1, then we rotate it twice, that we'll end up getting a reflection in, I can't remember which one it is, it's either L2 or L3. It would be a good idea if you have a look through that and work through that yourself. But this format here where we have this or this set notation is another way. So you need to be able to, you need to be familiar with both. Okay, now we can go to some of the questions that Benny asked. So D10 he asked about. Well, that's the symmetries of a 20-sided, a 10-sided regular polygon. I should just say, with this notation here, this is 10 and this is 10. I'm using the abstract algebra type definition. If you're more geometrically orientated, you're studying geometry, you may find that they use different notation. They may call this D20 or something like that. So anyway, I'll let you sort that out, as long as you know that the notation is not cast in absolute stone across all the different areas of mathematics. Okay, now the next thing that he asked me about was subgroups. I don't really have time to go through this fully, but you could see that for D3, I'll just give you some of them. Well, 1 is a subgroup. What else is a subgroup? Well, you could have 1 sigma squared. That would be a subgroup. You could also have 1 and tau. That would be a subgroup. And you could also have D3 itself is a subgroup. So these are all subgroups of D3. And I think from memory, the number of subgroups, I haven't done all the subgroups here, by the way. The number of subgroups, I think it's equal to tau n plus, sigma n plus tau n. Now here, the sigma and taus are arithmetic functions, nothing basically to do with the rotation and reflection. And this is the, I think this is right, don't quote me on this. I think it's the sum of the divisors of n plus the number of divisors of n. So all I'm hinting at here is that I think there's a reasonably simple formula for the number of subgroups. But if you work that out for D3, what I just showed you, you'll see that there are other subgroups. So that might be a good exercise for Benny and any others. Now, what about D2? Well, that is the dihedral group. That is a dihedral group, but it's not really a symmetry of a two-sided polygon, but you would use a line and then you would have the D2. Well, it's basically just 1 and the reflection, or I suppose you could say it's 1 or the rotation, but it's that simple. And what about D1? Well, similar sort of comments, but it's a dihedral group, but it's the symmetry of a point. And with a point, there's the only thing really is nothing changes. So the only sort of action, if you like, is leaving it unchanged. So you'll see them talk about the symmetries of a polygon. Clearly that doesn't apply for D2 and D1, but they're still dihedral groups, as I understand it. Okay, I think I've said enough. It's been a long video, so there's a heap of things here. I hope people can follow up themselves, exploring further the subgroups, maybe going back to what we said at the start, looking at formalizing what I've said in terms of isometries and symmetries, which you'll need the definitions for, the proper mathematical definitions. So I'll leave it there. Any questions, just let me know.